Okay, first thing, did anybody consider doing this by hand? Why not? It didn't have the little calculator icon, you know, this little thing.
There, now it has it.
Now it has it, and I guess there's not buttons all the way to the top.
It's time.
Yeah, you have to have glasses.
Yeah.
Okay, just so you know, I would like you to think through what you would have done had you not used your calculator to find the derivative. Why are we finding a derivative of f in the first place? Yeah, we need the slope of the tangent line to plug into our typical rule here. Okay. I'll show you that in a second, but let's do y1 first. What is y1? Yeah. So f of 4 is 5/3. And then x1 you guys are hyped up today. What the heck? All right, in terms of the slope, just plug it in your calculator, take the derivative at 4, and then we get negative 0.555. And plug that in here. How'd that go for you? Any questions from the homework?
Yes. Question 20.
All right, let's go look at that.
It's really one.
20, is it this one?
Yeah.
Okay.
They're not really.
All right, this is question 20 from your homework last night. Are we just going to have side conversations the whole day? Because that's going to be annoying. If you need to do that, you're fine, but just step outside so it's not distracting. All right, let f and g be functions defined as given here. Let h be the vertical distance between the graphs of f and g between 0, x is 0, and 2. Find the rate at which h changes with respect to x when x equals 1.5. Okay? So this, by the way, will be something that we do later. It's pretty cool, honestly. It allows you to do some pretty neat stuff outside of just calculus class, but we'll be able to find the area of this space in here, which is a very random shape, right? But we'll be able to just work through a process and find the area of that. We'll even be able eventually, this is cool too, to rotate that around, like the y-axis, for example, and we'll have this cool like 3D shape, like a funnel kind of, that we'll be able to find the volume of and do all sorts of stuff with. It's pretty neat, but we're not there yet, obviously. So this one is going to use something kind of like that. I didn't then erase. Get off there. There it goes. How do we find, it says let h be the vertical distance between the graphs. So h of x is defined by what? Yeah, so it's f minus g, which then we can plug in the actual function rules. And we're going specifically at 1.5. So what's the rate of, let's see, the rate at which h changes, so the rate that that vertical distance is changing with respect to x sounds like a what?
Ratio.
No. Rate of change is also called a derivative. Yep. Okay, so this, we want dh dx, which means, and we want to evaluate this specifically at x equals 1.5. And we're going to use a calculator for that, of course. So just punch all that in there. Do you want me to do that, or are you good with that part? Okay. Any other questions on the homework? Yeah. 22. All right, given the function there, which of the following values of x has a tangent line with the greatest slope? How do we, this is a calculator one. Did you do it on there? Okay. So let me go enter that, x cubed e to the x sine x. Here's how I would do this one. Go to the grapher, and we're going to say x cubed, that's not it, cubed minus e to the, oh, I hate it how it does that. Go down, minus e to the x minus, what was the last part? Minus sine x. Okay. All right, so there's this weird looking graph. I don't know if you remember this, but remember, if you want, you can just hit the plus and minus buttons to zoom in and out. It's so much nicer than TI. Like if I want to zoom out and see what this looks like, plus and minus, okay? And then navigate, if I go up to navigate, allows me to like scroll around. So this is what this thing looks like. Okay, question again says, which of the following values of x has a tangent line with the greatest slope? In other words, we're looking for something that's the most steep when we draw a tangent line in. And where do you think that occurs? You know what? Give me a second to take a little screenshot of this guy. See if I can do it fast. Okay. Copy. Can I do it? I think so. Paste. Sweet. There we go. All right. So just in your brain, you can start thinking about tangent lines. So like, obviously ones down here are pretty darn steep, right? Versus like one here is not as steep, etc. So let's just look at these values. -3, that's where I drew the first one and said pretty steep. -1 is probably going to be in here somewhere. It's not that steep. 0, definitely not. 1, definitely not. And then 3 is going to be kind of up here. It's pretty steep, but not as steep as this one down here. So that's kind of the process. Does that help? Okay. Any others you'd like to do? Okay. All right. How's definition of derivatives going for you? Give me a fist to 5 on your evaluation. Basically the first 3 sections of this unit. Okay, we are so close. It looks good. You can put them down. Thank you. We're so close to starting into the rules and not having to do that big, long, ugly process for a derivative. We will do that on Thursday. But go ahead to go to 2.4. And here's that graph. Oh my word, are you serious? I had it right there and it just reset. That's annoying. Go ahead and try to write an equation for the one. You have a little snippet of it. Go on line 1, write an equation for that graph that you see there, please. Well, I type it back in. Whoop, that's not what I want. That one right there, yeah. Give me a second. That's really annoying. Does anybody know why that would have happened? Just navigating away from that tab took me, it like reset it. That's.
Wait, what happened?
I had it all entered in, everything was all set up, and then it just went away.
Or maybe just to save like on memory, you could just clear it back, just for it to slow down. If you're not using that,
I'm just using it online. I don't know. That's really annoying. Okay, let's try this again then. So here's that graph that you're seeing there. What did everybody write? 2x plus 1. All right, so that's what you should have in line 1. 2x plus 1. Okay, now I'm going to show the grid line or the axis numbers. Rewrite your equation based on that, please. Because we didn't have those, so now we do. Okay, what are you thinking now? Still 2x, right? Like that didn't change. I just put on numbers, so the 2x part shouldn't have changed. But now what is our y-intercept? 0.001. So 2x plus 0.001 on that second line. Now that's a totally different line than what we wrote the first time, isn't it? Because now we had more information that it was not, we assumed in the first case that it was scaled by ones, but now that we know it's not, we have a different line. Okay, let me show you what this actually is. Okay, what kind of function is it actually? Some sort of a trigonometric sine curve, right? So a periodic function. But when we zoom way in, it looked like a what? It looked linear, okay? That could be true even if we zoom in on one of these curvy parts. And, no, that's not what I meant to do. Gosh, this thing is annoying. Okay. Like I'm looking at the max. If we zoom in far enough to that thing, do you see how it looks like a what?
Just a line.
Just a horizontal line. So that's true of any part of this graph. If we zoom in far enough, we're going to see that it looks linear. Okay? So the title of your section today is Differentiability and Continuity. So we've studied continuity. In fact, let's do a quick review. How do we know if something is continuous? In calculus, not in algebra 2. In other words, if I said prove it. Okay, I don't want the basic fly-by-night description, guys. Study your stuff so you can tell me those criteria. There's 3 of them. Well, technically it's 2. Okay, so the limit, if we go back to the 3 is how we wrote it. It's f of x exists, or f of a, if we want to say it. Let's put an a in there just so we keep it clear. F of a exists. The limit as x approaches a also exists. And then the true test of continuity is putting those together. The limit as x approaches a from the left equals the limit as x approaches a from the right, which is the other way of saying the limit exists. And what else does that have to equal? It has to equal f of a. Okay? Really, it boils down to those 2 pieces. Really lock that in. You probably will have a test question on your AP test in May that is going to have you use that. Okay? Yeah.
You do have a mock?
You'll have a mock, yeah. It's a good mock, too. At least the one I have that I make for you. It's a good one.
Thank you.
Yeah. All right, so let me fill these out just to get us caught up. But okay, so that function that I showed you is actually this. Write it down. Sine 2x plus 0.001. That was the actual equation of that graph. And we know that a sine curve is continuous, but differentiable, that's the new one. So differentiable, we're going to actually study that or talk about it a fair bit. Do you guys remember, and I don't want to pull it up just because it would take a second, but on your question, on your test question where you had to use the intermediate value theorem about VA of t of the train, remember that question? And it said in the text, like in the prompt for the problem, it said VA is a differentiable function. At that point, we had no clue what that meant. A lot of you said it's continuous, which was good because that was true, even though it didn't say that. But these two go together pretty well hand in hand. That doesn't mean the same thing. That's not what I said. They just go together. So let's define what differentiability means, or differentiable. It means that the derivative, like just as a basic definition, the derivative exists for each point in the domain of the function. Okay, but how do we know if the derivative exists? So the graph must be a smooth line or curve in order for the derivative to exist. So here's some fails for that. Number one, if we have a discontinuity. Why would that discontinuity? Why would that make the derivative fail? Like, let's say we have some hole in our graph. Why is that not working to take the derivative? True, because we don't even have a point there, right? But that point doesn't exist in the domain of the graph. Okay, that would be true also for any jump discontinuities. There is no derivative there. Okay, this one is new. I mentioned it the other day. If you have a corner or cusp, not super technical words, but let's say we have something that looks like this. That point right there is called a cusp, and it is not differentiable. I'll explain why in a second. What about this function? See if you remember the name of it. Yeah, it has a corner, right? So that sharp point, the vertex of that absolute value graph, is not differentiable at that point. It's differentiable elsewhere, but not at that point. Okay, and then number 3 is a vertical tangent line. So think of a graph. Let's make a little axis here. Something like this. Like almost a cube root function, something like that. But that point, somewhere in here, would have a vertical tangent line. What's the slope of a vertical line? It's undefined, right? You remember the M is our letter for slope. Okay, so if we have an undefined slope, then remember what the slope of the tangent line is called? Everybody? Slope of the tangent line is called the derivative, right? That's the derivative of that function at that point. So if our slope is undefined, so is our derivative. It's undefined as well. All right. I want you to write this phrase, so underline this piece. It looks like a line if you zoomed in. That's why we just looked at that weird function, the sine 2x one. We call this local linearity. So if it looks like, if it at any point doesn't look like a line when you zoom in, then it's not differentiable. And of course, we're not talking about a straight up and down line like the third point there. So local linearity is what you're looking for. Now, you're not going to be able to zoom in on all these, okay? So you'll need to know some things about functions. Like is this a differentiable function? Y equals x squared. Yeah, you know, because it's a nice smooth curve. There's no jumps or anything, right? Same with like this one. Y equals, let's just call it e to the x. It's differentiable. Okay? We know that we could zoom in on any point and it would look linear, as well as the fact that it's smooth. There's going to be more to this, but for now, this is kind of our discussion of it. What's the definition of a derivative? Up here, I want you to write this down. So you can check differentiability. Are you picking up that differentiability, differentiate, differentiable, all of those have to do with taking a derivative? Are you picking that up? So you can check differentiability by checking the definition, which everybody hates. From the left and right. What's the definition? So f prime of x is defined to be what? Guys need to have this memorized. Study that stuff. No, you forgot something. You forgot something. Okay, flip back a couple pages if you don't know. Just get eyes on it again. Definition of a derivative. That was 2.2. Should be right near the top. I can't remember exactly where on the page that was. Maybe it was towards the bottom. Yeah, it was at the bottom of 2.2. Definition of a derivative. What is Trevor forgetting? He's on the right track, but forgetting. The limit as h approaches 0 of f of x plus h minus f of x over h. Okay. So we can check the left and right. So approach 0 from the left, approach 0 from the right. That kind of idea. Okay. We're going to do that here in a second, which is why I wanted us to not take too long. Man, this class, this week goes by too fast. Let's start with some easy ones. I'm going to come back to that in a second. Let's start with some easy examples. So identify points where the function is not continuous and or not differentiable. Let's just run through these. I think this one should be pretty easy. Where is it? Let's just go left to right. Go.
Not
Where? Okay, -3, not continuous. Okay. Do we need to say not differentiable? Well, look right up here. If there's a discontinuity, is it differentiable? No. So this one takes care of that. Okay, what's the next point?
x equals
Is it continuous there? Yeah, thinking of limits, the limit from the left is 0, the limit from the right is 0, and the function's value is 0. So yes, it's continuous, but it is not differentiable because no matter how far we zoom in on that, it's going to be a point. Okay, next point. X equals 2. And what's true there? Yep, let's just abbreviate now. Next point. Not continuous. So is it differentiable there? No. Okay. I don't want this to get confused. So if we need to, let's write that it's that as well. So, and I'm going to put that on this first one. Also not differentiable. Okay. True or false? Let's see. Don't shout this out. I just want you to think about your answer, and then I'll ask everybody at the same time. Differentiability implies continuity, meaning if it's differentiable, it is continuous. If you need to write that interpretation, go ahead. If I tell you, like I did on your test, this function is differentiable, does that say that it's also continuous? For sure. Everybody answer? Yes, that's true. Okay, this is the converse, if you remember back to geometry days. So we're just flipping it. If it's continuous, Chloe, I feel like I'm just walking. Okay. If it's continuous, it's differentiable. That's the converse of the original statement. Is that true? Okay, we saw those two cusps right here and here. False, right? The function was continuous but not differentiable, so this is false. Okay. You don't have this stuff, so just look at the screen. Feel free to write it down. I just answered that. Okay. This got cut off, but it's just function f of x. This is a function. It says it is differentiable at x equals a if. So this is what we wrote in that top right corner. We're going to go add this in there in just a second. So if both of the one-sided derivatives or one-sided limits are the same. In other words, if that limit exists. Notice this one is using the other definition of a derivative that we saw was nicer in some cases. So it's the f of x one. I think you will like it better. We'll go write it. I promise we'll go write it in your notes. So use the limit definition, and for this, definitely use I'll write it here just because we don't necessarily know it, but use this one instead of the other one. It'll be faster. So to determine if g of x equals x squared is differentiable at x equals negative 1. Do we know it's differentiable at x equals negative 1? We already said this today that it is, right? Why? Because it's a nice smooth parabola. It's not going to have any jumps, any cusps, any vertical tangents or anything like that, okay? So let's use this to prove that it is. If you want to write this down, let's use this kind of as an example. So we're approaching negative 1 from the left. And remember in this definition, f of x is just x squared, okay? So x squared minus, and then f of a. What is f of a? Or f of negative 1 in this case. Yeah, so minus 1 over x minus negative 1. Okay, what can we do with this? Yeah, so this is, again, remember to use your limit notation until you plug in. This top becomes x plus 1 over x, or times x minus 1. And then the bottom is x plus 1. Okay? Those cancel. And I think I'm just going to plug in to save some writing. So -1 plus negative, or -1 minus 1, however you want to think about it, is -2. Okay? And then does that change at all for the other side in this case? Like if I say limit, we need to go check limit as x approaches -1 from the right. Am I changing anything in there? No, it's not like the absolute value function where we have the negative and the positive version, right? So this looks the same. So dot, dot, dot equals -2. So the limit exists. The limit exists. So it is differentiable. Now look at this next one. It's piecewise. What do you think is going to happen there, just as an example? If I come into +1 from the left, you can probably just tell me what that is. It's 2. The limit from the right of h, limit as x approaches 1 from the right, is what? 2. So same thing, right? Had this been like -2, or maybe if our function rule had been -1 and the limits weren't the same, we would see a jump. And so would the derivative exist there? Would it be differentiable there? No. Okay. Questions on that one? Okay. Before I forget, since I told you we were going to do this, right up here. Let's go ahead and write this. You can use either one. I think you'll probably like this one better in most cases. The blue one. But you can use either one. And if you forgot how to do that, go back and look at 2.1. We had an example of both of these. Okay? All right, let me show you a couple more examples. We already talked about that. But let me show you the work for it. Everybody look here, please, just to save a minute. So we said that there's a corner for the absolute value function at x equals 0, but here's the work that proves it. I know it got kind of cut off a little bit, but remember for absolute value, we drop the absolute value and make one of them negative and make the other one positive, like the two cases. So in here, from the left, we make it negative. From the right, it's just positive. And we get two different values, -1 and 1, which proves that the limit doesn't exist there in terms of our definition of the derivative, I mean. So it is not differentiable. Okay? How about square root? What do you think of that one? I don't know if I have that one. I don't. Here's a really important point that I want you to write on your notes. Please. So write it back on your note packet. You can't take a derivative at an end point. Why?
Because it has to be a line, it can't be a point.
It what?
The derivative. It has to be a line, it can't be a point.
Well, we take derivative, we have slopes at points elsewhere, right? Like for example, if I wanted to know the slope at this point right here, it definitely exists. So let's be a little bit more specific.
It's kind of like the idea of a limit. There's no limit from this.
Yeah, there's nothing coming, good job. That's exactly right. Like there's no limit coming in from one side, right? It's only one side here. So you can't take a derivative at an endpoint. So this function would be differentiable everywhere except for it's at the beginning. Okay, what we would call that. I'm gonna maybe skip that for now. That'll be your warm-up tomorrow or Thursday. Okay, I think that's good since we're out of time. So questions on differentiability versus continuity and how to check. Okay. Do number 3 and the test prep. And I'm going to upload a AP Classroom assignment for you to do. So look for that.